Now, let us get into the anchorage slip loss in a post tension member. Okay. Now, what is an anchorage slip loss? In post tension members, again wedge will slip. When you do that, the wedge will go and sit on the anchorage, and then the anchorage movement will happen in the anchorage block. That will create a loss in pre-stress due to the reduced tendon length. Now, the total anchorage slip, because typically you will have this wedges, right? The anchors have to go and bite the strand, and then by the time it can go and grab the strand, there is going to be slip. In addition to that, there is also going to be deformation in the anchorage block itself. So, these total together we call them as an anchorage slip. That will reduce the net effective stretching that we are providing it on the strand. Okay. So, typically the total anchorage slip depends upon the type of anchorage system. In the absence of manufacturer's data, some typical values of these systems can be used. For example, for Fresnel system, depending upon whether you are having 5 mm diastrand or 8 mm diastrand, the anchorage slip values can be taken as 4 mm or 6 mm. For Magnell system, it is 8 mm, and Dividac system, it is 1 mm. These are all the recommended values of the slip that typically in design calculations we use. Now, why is it important? Again, from anchorage slip point of view, there is something called reverse friction occurs. Now, when the anchorage slip is happening, there will be a sudden loss in pre-stressing force. From jacking force, it will drop to a certain value, and then it will try to recover that force, right. So, this is the phenomena called reverse friction effect. It will try to nullify the force that will be lost due to the anchorage slip, because it is like a friction, right. It is going to act opposite direction. So, now there is a sudden loss in pre-stress force, it will try to regain. So, because of that, there will be a reverse friction effect. Okay. So, that is what we are trying to see. In this case, if you see here, this is a P naught is the initial force, and this keep on reducing due to the curvature and wobble effect. But initially, this delta P that is happening because of the anchorage slip. This loss is happening from anchorage slip. Now, at a certain distance called L set, because why this, if you see here, now at this location the initial force is P naught minus delta P, right, and this value will keep on, now you see if this value will keep on increasing up to a certain value. This increase is happening because of reverse friction effect. Okay. As you say, there is a sudden loss that is happening because of anchorage, and then the system tries to regain that lost force. So, the friction effect will now act in the opposite direction, that is why it is called as reverse friction effect. Okay. Now, this is the overall effect, what we saw previously is the overall effect. Now, at a certain distance L set, the force that is recovery that is happening due to reverse friction and the overall pre-stressing loss that is happening because of the friction from curvature and wobble effect, they will reach the same value. That means, at a distance at L set, this force, right, if you see Px prime after set, and both of them will be same. So, at a distance x is equal to setting length, the force that is regained due to reverse friction and the overall force loss that is happening because of the curvature and wobble effect, they will reach the same value. So, why this is important is, we need to understand this force variation diagram clearly, so that in that first segment where this reverse friction is happening, we can account for the exact pre-stressing force in the design of the post tension system. This can be sometimes what will happen especially at the support location. If the delta P is significant, then it will reduce the beneficial effects of pre-stressing, and also usually at the support location the shear will be dominant, and if your pre-stressing force is not correctly accounted in your design calculations, you may have unsafe, I should say, you may end up with a not a safe design. So, we should be careful in accounting exactly this force variation diagram, right. So, this is Px beyond okay. Now, what is L set? L set is nothing but is a length from stretching and at which the Px will be equal to Px prime. So, now you see here Px, this is the equation because of the, again the original curvature and wobble effect. Now, this the green color what we are seeing here, this is your Px prime equation. So, there are two effects, Px will be equal to Px prime at x is equal to L set, that is what we are trying to see. Now, from our calculations point of view, now we need to find out what is the equation for L set and what is the equation for this delta P. So, that is what we are interested in calculating. Now, you see here, let us say at force at L set will become same considering the anchorage slip along with the reverse friction and force loss due to curvature and wobble effect. So, that means at this distance x is equal to L set, Px will become Px prime, right. So, now let us look at now. We can use both the equation Px is equal to Px prime. Now, how do we do that? The overall equation we know that Px is nothing but P naught into e to the power of minus eta into L set, right. Now, why that eta, that what we are doing is here eta, if you see here eta in general I am writing that as mu alpha plus kx. Now, alpha is also function of x, right. So, everything can be written as eta into L set. So, the x can be taken out and you can write that as eta into L set, okay. So, that is the reason that we are writing eta is nothing but mu alpha plus kx. I am putting as a one simple the notation as eta, which represents both the curvature effect as well as the wobble effect. Alpha, the cable change profile is also can be written as a function of x. So, in that way eta can be written as eta into L set, which is basically your mu alpha plus kx, right. So, the original pre-stressing force variation is P naught into e to the power of minus eta L set. Now, what is this? You see Px prime expression. Now, at this location the initial pre-stressing force as we have discussed is nothing but P naught minus delta P. So, this is the initial pre-stressing force. So, this is your initial pre-stressing force when I am considering the reverse friction effect. So, P naught is nothing but P naught minus delta P when I am considering the reverse friction effect. Now, let us say that this is now the friction is acting in the opposite direction. So, it is going to be not e to the power of minus eta L set, it is going to be e to the power of plus eta prime L set, right. So, if I take this eta prime L set in the other direction, then I can write this as P naught into e to the power of minus eta plus eta prime into L set. The L set L can be taken out, right, because again alpha and x, alpha is function of x is the length distance at which you are considering. So, L can be taken out, that is the reason we are writing, because we are doing calculation at x is equal to L set. So, I am put L set here, right. So, then you can see that P naught minus delta P can be written as again from Taylor series expansion as P naught into 1 minus eta plus eta prime times L set, right. Now, when you simplify this, I can find delta P as P naught into eta plus eta prime into L set. So, when you do that, again this P naught and P naught will get cancelled and then you can find an expression for delta P like this. Now, delta P now can be expressed as P naught into eta into L set into 1 plus eta prime by eta. Now, let us assume that the friction coefficient that is happening for the overall friction loss and the reverse friction is one and the same. So, that means I am going to say that eta prime is equal to eta. So, when you do that, I can find a simple expression for delta P as 2 into P naught into eta into L set. Now, eta is nothing but again this eta is nothing but mu alpha plus kx, again then I can put that expression eta L, L can be taken out and then you can find the value for that. And so, in this way you can find a simple expression for your delta P as 2 into P naught into L set. Now, let us see slip deformation and set length. Now, we should also calculate what is the slip deformation and now we have found an expression for delta P, and P naught I know, and eta is your friction coefficient and wobble coefficient and the cable profile, all those things we can calculate. Also I do not know what is setting length. So, to calculate delta P, I need to know what is your setting length as well. So, we need to now find an expression for your setting length. Now, let us see what is the slip deformation and set length equation. Now, we know what is the slip deformation. What is slip deformation is, let us say that if you go back to this force, what is that force loss that is created? Now, we know the deformation is nothing but PL by AE. Now, what is that slip deformation that it is caused by? Some delta P average force. Now, what is delta P average? It is nothing but delta P by 2, right. So, that means delta S will become delta P by 2 times L set, because this is happening over a length of L set divided by AP into EP. So, that is what we have it here, right. So, we can write that as this. Now, if I write the expression for L set in here, then P naught into eta into L set times 1 plus eta prime by eta. And then if I substitute, so L is here also you have L set, right. So, L set square. Now, I can find an expression for L set square like this. Then if you simplify that, if you put eta prime equal to eta, then you will find that L set will be equal to delta S slip deformation into EP divided by P naught into eta. Now, what is this P naught eta? It is nothing but average force loss in the span being considered. Okay. So, let us look at it. So, if I know the value for P naught, which I know, right, and delta S is a slip deformation that is typically given from the manufacturer's data. I know what are the area of preceding steel, what are the EP. Then if I somehow can calculate this P naught eta, which is nothing but average force loss in the span, there where you are assuming that the del set is going to happen, then I can calculate my setting length. Using this simple expression, we can do that. So, this is what I said, typically we assume that friction coefficient for both reverse friction and the normal friction is same. So, that is the reason that we can simplify that L set in this simplified form, right. So, let us look at now, so from the previous example, so basically if you see, we have looked at very important things. One is this force loss that is happening because of the anchorage slip, and up to how long setting length the reverse friction will act, right. At L set, Px and will become Px prime. So, I need to find out up to what length this is happening, this reverse friction effect. After that, it gets nullified, right. The overall effect will now take in. So, using these values, I can clearly establish a force variation diagram. So, which is very important from design point of view. That is the reason we have to see what is the effect of anchorage slip and what is the reverse friction, why is it at x is equal to L set, this this is important to find also the expression for your setting length, so that you can use the exact forces in your design. Okay, so we have discussed this. Now, let us look at this force variation diagram. Again, if you go back, typically when you do this, this is your again live end, this is jacking end, and you know that the force is going to be higher here, and if you go to the other end, it is going to be lower here. And right after when you anchor, this is what we said, there is going to be delta P, and then the reverse friction will happen, and at this point now you know that this is nothing but your L set, right. This is for the anchorage slip at the right end. Now, when you do the same thing, so that is what we did. When you have like say 10 tendons, 5 tendons I stretch it from one end, and then 5 tendons I stretch it from the other end. So, in this process what will happen here is, again when I do the stretching from the left end, there will be a delta P, there will be a reverse friction again, and certain distance it will catch on, right. Then if you then once you have the anchorage slip, okay, this is only from stretching from the left end. Once you anchor after anchorage slip, then you will have this kind of a force that will go like this. Okay. right. So, this is your delta P that is happening here. Okay. So, overall if you look at it here, when you do the stretching from both ends, you kind of get an average force. Okay. So, that is very important. That is the reason typically wherever it is possible, you try to make sure that you stretch it from both ends so that you end up with an average pre-stressing force. Otherwise, what we have to do is, as we explained in the previous slides, we have to do the stressing in multiple levels. You stress it to 80, you release it to 60, and then again you go back to 70. That way again you will have average pre-stressing force. Okay. Now, let us quickly look at one example problem to appreciate all the things that we have discussed so far. And this is again the same problem that we did for the understanding the friction loss effect. So, let us use the same thing, and this is what we have previously we have done. Px at x is equal to 0 will be 3134, this is the initial jacking force, and then at mid span location of the second span you will have a force of 2675, right. Now, what is the P average? So, because why we are looking at here is the P averages. Now, using this we are going to look at what is your delta P and what is your slip deformation and so on. Now, to use this setting length calculations, I need to calculate what is the average force, right. Now, how do I get my average force? You see here, if you go back to this, at each end we know this, and we know the distance between them also, right. So, you kind of take average force, so 3134 plus 3064 and multiply by 8, because that is a span. The next one is 3061 plus 2942, and it is acting over a span of 8, and then 2942 2861, it is acting over a span of distance of 2.5, and then next one is also 2.5, next one is 7. If you take average of all these things and divide by the 28, then you get your average pre-stressing force as 2937.4, and now using that I can calculate the elongation at each stretching end, and we know that elongation is PL by AE, and P average times length divided by AP into EP will give me a stretching of 170.85 millimeter. You see here, for a span of 28 meters, you get a very large stretching of 170.85 millimeter, right. So, this is very high. So, basically pre-stressing steel acts like a rubber band, it is really stretching, right. So, it is a stretching is in the order of 170 millimeter, which is quite high. Now, we can also see that after anchorage, the effect of anchorage slip is present up to setting length, and the value of setting length due to anchorage slip 4 millimeter can be calculated as follows. Now, L set we have already derived a formula, which is delta S into AP into EP by P naught eta. Now, what is P naught eta? P naught eta is nothing but average force loss per unit length in the first segment AC. Now, that is what I said, P naught eta is the average force loss. Average force loss per unit length. Okay. So, if you go back to that, the first force was 3134, at span C it was 2942. If you divide that average by 16 meter, I get 12 Newton per millimeter. If I put that value here, and I get my setting length as 12.67 meters. Okay. If you go back, this is what the setting length was, right. So, the drop in pre-stressing force again because of the anchorage slip, again 2 into P naught into eta into L set. Eta already we have calculated as 12 Newton per millimeter, L set is 12.67 millimeter meter, which is 12,670 millimeter, and 2 P naught in eta is what, 12. So, you get your delta PS 304.08 kilonewton. Now, the net what is going to be left is, after the loss, it is going to be 3134 minus 304.08, which gives me 2829.92 kilonewton, and we can also plot this, the force variation diagram. Now that we have calculated delta P, we have calculated the setting length. So, we can use it and we can calculate the force variation diagram like this. So, this is before anchorage slip loss. Okay. You can see that because of curvature and friction, the pre-stressing force is going to keep changing. Now, the change, the slope is going to be different for different segments, because the curvature of each segment is different. That is the reason the slope, it is not going to be linear. It is going to be, the slope for each segment is going to be different, right. And then right after your anchorage slip loss, you have this is your delta P that is happening, and here your reverse friction starts, and this is nothing but your setting length L set, which we calculated to be 12.67 meter, right. So, okay, so let us summarize this module. So, we have discussed about sectional properties and losses in pre-stress were introduced, and elastic shortening losses in pre-tension and post-tension members were estimated, and we also did calculations using an example problem on how to calculate the friction losses and anchorage losses in post-tension system, and we also did how to plot this force variation diagram, which is very important from design point of view. So, with that we will end this module. Thank you very much for your participation. I will see you soon. Thank you.